Okay, welcome back everyone. In this series of videos, we're going to be talking about the universal law of gravity. And so we're going to start with Newton's law of gravity. And what we want to figure out in this segment is how we can calculate the gravitational force between two objects. So Newton's universal law of gravity simply states that the gravitational force is equal to the product of two masses m1 and m2 divided by the square of the distance between them. And Newton also knew that there was some sort of constant g which had to go in front of the expression m1 m2 over r squared, but he didn't really understand or wasn't able to figure out what that g was. And that was left to Cavendish to figure out a couple of years later. So universal law of gravity is a radial force, so that's why we have the r hat vector and the negative sign, showing that if I have two masses, the force of gravity is on a line connecting them. Okay, so it's important to note that it is a vector which points in the negative r hat direction. So it goes from m1 to m2 or vice versa. Okay? And it's an inverse square law. So we'll talk a little bit more about that in a moment. And this constant, big G, is 6.67 times 10 to the minus 11th. And in order to make these units come out, we got to have newtons up top to get newtons on the left. And then we have to cancel out meters squared and kilograms squared. Okay, now the law of gravity obeys Newton's third law. So the force of gravity from one object on another is the same even if the particles have very different masses. So the magnitude of the force is the same. And the other thing, which we're going to actually prove later on, is that the gravitational force between two symmetric masses, m1 and m2, if they're spherical, it acts the same as though all the mass were concentrated at the sphere's center. And so we'll talk more about this in an upcoming video. So for now, we want to calculate the gravitational force of attraction on a person from their very attractive physics book. Okay, so we'll set this up, and we have an 80 kilogram person. And when I was in college, we used to joke that we would approximate a cow as being a sphere, so a spherical cow. And this is a spherical person. Because if you try to actually calculate the force of gravity on a person with all their arms and legs, then it gets kind of wonky. So we're just going to pretend like we have point particles. Okay, so our force of gravity is going to be equal to g m1 m2 over r squared. Now r is what we call a center to center distance. So it's from the center of one object to the center of the other. So we can set this up, and this force of gravity will be big G, which is 6.67 times 10 to the minus 11th newtons meters squared over kilograms squared. And I'm going to write it this time just so you can see it, but in the future we won't write it, okay? And then we have 80 kilograms and 1 kilogram, so that's how those kilograms cancel. And then that's all divided by 1.0 meters quantity squared, which is going to cancel with those meters. Make sure that you actually square this number, the 1.0, before you cancel out the units. Okay, so don't cross out this square here because you might forget to apply that to the number down there. So in any case, that gets me a force of gravity that's about 5.34 times 10 to the negative 9th newtons, which in real life terms is so small that we can pretty much ignore it. It's many, many factors of 10 smaller than any frictional forces, which is why objects in real life don't just start floating towards each other or sliding around. Okay, now this is the force of attraction on the person by the book, but that's equal to the opposite of the force of gravity on the book by the person. So if this is the person and this is the book. Okay, and that's Newton's third law in action. the force of A on B is equal to the negative force of B on A. And so which one has more acceleration? Well, the acceleration depends on the mass of the object because F equals ma. So if the gravitational force is the only force we're dealing with, then the acceleration of the book will be the force of gravity divided by the mass of the book, and the acceleration of the person will be the force of gravity divided by the mass of the person. And this is going to be over 1, and this is going to be over 80, so the acceleration of the book will be greater. And we could calculate that, we don't have to, but the book's going to have a much larger acceleration. Okay, now because gravity is a force, it also obeys superposition. And so when you have two or more forces that are acting on an object, you add the forces as vectors to determine the net or total force. And you can set up a table if it's easier for you. Okay, so we calculate F1 and we split it into x and y components. So F1 is between this object here and this object here. Hopefully you can see that. And then we split that into x and y components, and we do the same thing with F2, which is between this object and this object right here. And then we add x and y components to get the total force. Okay, so we're going to do this as an example in just a moment, but if we label these as, let's just get a different color. Okay, so object A, object B, and object C, then we would have the force between A and B right here, and it would be split into x and y components, and the force between A and C right here, and it would have x and y components. This would be if we want to find F net acting on A, and then we would get our totals, and we would make a new triangle. Okay, so let's actually do that. Okay, we want to find the total force F acting on this object right here. Oh, so this guy. Okay, so we're going to go ahead and calculate these forces. Okay, and we can say that F1, and let's call this A, B, and C again. So F1 is actually FAB, and that's actually equal to G, and then MA, MB over RAB squared. Okay, so that's 6.67 times 10 to the minus 11th, and we're not going to put the units in anymore. That's 1 times 10 to the 30th kilograms, and then 8 times 10 to the 30th kilograms. Just make sure that you have everything in kilograms and meters. Okay, and then the distance here is actually going to be 2 times 10 to the 12th meters times root 2, because we have the hypotenuse of this triangle here, and that is going to be squared. Okay, so that's going to give us a total force of, looks like about 6.67 times 10 to the 8th. Okay, and let's just check that real quick. Okay, and actually I hit a wrong button somewhere. It's actually to the 25th. Okay, so that makes sense because we have extremely large values in this. Okay, likewise we can find F2, which is really FAC, and we can plug this in, and since basically the only difference is that we're a factor of 1 over root 2 closer, we can just take this force and multiply it by 2, so it's going to be 1.33 times 10 to the 26 newtons. So you can also, if you don't really believe me, just plug in G and then MA and MC, and then this is just going to be RAC squared, and RAC is just going to be 2 times 10 to the 12th. Okay, so now we're going to set up that table. Okay, and we're going to have x and y components. This will be the force of A on B. This will be the force of A on C. And rather than putting in these numbers because they're really kind of ugly, okay, we're just going to call this is going to be FAB, and this is going to be FAC. So then FAB would have an x component of FAB cosine 45, or times root 2 over 2, and FAY, FAB in the y direction, would also be times root 2 over 2. We have a 45, 45, 90 triangle here, so it's easy numbers. Okay, then FAC would be all of FAC in the x direction and then 0 in the y direction. Okay, and then from this you would find your totals. So whatever that is, we would call that F total in the x direction and F total in the y direction. And that's going to give us a lot in the x direction and a little bit in the y. And we're going to find our F net and our angle from that. So, and that's this vector F right here that you can see that they're drawing with the parallelogram rule for adding vectors. So we're not going to go into the details of this anymore, but this is how you set it up. Okay, so next time we're going to talk about the concept of weight and gravitational field.